In the last video, we found the area bounded by these two curves, and we found that it was kind of a tough process because the top of the curve didn't change throughout, the top of the shape didn't change throughout the length of the integral. The bottom did, right? As we went from 0 all the way to 4 for x, that bottom changed from the orange curve to the purple line. So what we're going to try now is kind of changing our perspective, right? We're used to finding these integrals with respect to x, but there's no rule saying we have to do that, right? We can instead find these integrals with respect to y, which would make our rectangles sideways instead, right? So if we take a look at this, then the dimensions of this rectangle, this little bitty change right here, this infinitely small change, is not a change in x anymore. This is a change in y. And so we're going to have an integral with a dy instead of a dx, okay? And what are we going to multiply it by? Well, we're not going to multiply by the height of the rectangle because the height is dy. We're going to multiply it by the width. And in order to figure out the distance from one end to the other, we're not going to do top minus bottom anymore. We're still going to do big one minus small one, but it's going to be the larger one is now on the right, and the smaller one is going to be on the left. So right minus left. Okay. Now remember that these are going to be x values, right? The x value starts at 1, 2, 3, 4 for these right endpoints, and then for the left endpoints it starts at 1, goes down to 0, and then goes back up to 4. So we're talking about x values that should go in here, but we're not going to put x values in here. We're going to put x values in terms of y, just like we used to be putting y values in here in terms of x. So we want to know what the right side is in terms of y, not what does y equal in terms of x, but what does x equal in terms of y. So that's an important distinction. So instead of saying y equals x minus 2, we're going to add that 2 to the other side and realize that this curve right here, this line, is x equals y plus 2. Okay, so that's the x value of every single point on this line in terms of y. And we don't have to do anything to this equation because it's already x in terms of y, right? X equals y squared. So our right x value is y plus 2, and our left x value is y squared. So right minus left is y plus 2 minus y squared. Now, the other thing we need to remember is that our y values are changing, not our x values are changing. So we're going to start at the bottom, right? That's the lowest part of this, which is at y equals -1, and we're going to keep on stacking those rectangles up all the way until we get to this point right here, not at x equals 4, but at y equals 2. So it's very important to remember that these numbers that go over here are counting the starting and ending points for, in this case, y, because that is our variable that we're integrating with respect to, our change in y. So that's a pretty significant change that we want to make sure we're aware of. So this is a much easier process than the last one because we didn't have to break it up into two integrals. We just have one integral. Not only that, we don't have any square roots, so that's kind of nice. So when we integrate this, we get 1/2 y squared plus 2y minus 1/3 y cubed. We'll evaluate that antiderivative at 2. We'll evaluate it at -1, and we'll subtract the 2. So 1/2 of 2 squared plus 2 times 2 minus 1/3 times 2 cubed. That's the antiderivative evaluated at 2. Then we'll subtract the antiderivative evaluated at -1. All right, so this is 1/2 of 4. This is 2 times 2. This is 8 times 1/3, so that's the first bit. The second bit, well, this negative turns positive because of the even exponent. This is a -2, and this negative does not turn negative because it's an odd exponent, so it's a -1 times -1/3, so that does turn positive to plus 1/3. And then we can simplify from there. We get 6 minus 8 thirds, or 18 thirds minus 8 thirds, which is 10 thirds. Here we've got 3, I'll write this one out, 3/6 minus 12/6 plus 2/6 is 5 minus 12 is 7, so minus negative 7/6. I think I did that right. Let me double check. Negative 9 plus 2 is negative 7. That seems correct to me. So when we work that out, well, we need to get a common denominator, so that's going to be 20 plus 7 over 6, 27 over 6. That sounds like the same answer we got last time. When we divide by 3, we get 9/2. Divide by 3 on the top, divide by 3 on the bottom. It's good that we're getting the same answer we got before because we're finding the same thing as we found before, the same area, this area of the same shape. But we're using a more efficient process by differentiating with respect to y instead of differentiating with respect to x. Nope, integrating, excuse me, we're going backwards. All right, and here we've got one last, well, not one last, we've got one more problem here where we've got a cubic. This is our first cubic of the day, that's fine. And that cubic and that linear function intersect at 3 points. So we actually have 2 different regions. And I guess one thing we can realize here is that region 1 and region 2 are both created by the same curve, but notice the key difference here is that the top is the line f of x for region 1, but then it's the bottom of region 2, so the bottom equals f of x for region 2. So the top and the bottom switch when we go from region 1 to region 2. So over here, the bottom equals the cubic, which is g of x, whereas over here, that cubic goes above the line, so it's the top. The top equals g of x here. So the picture helps us out tremendously because we can see these points of intersection very clearly. We've got when x equals -1, when x equals +1, and when x equals +2. So if we're going to find the area of region 1, we're going to integrate from -1 to +1. Of top minus bottom is going to be f of x minus g of x. That's going to be the area of region 1. And then the area of region 2, here we go, purple. The area of region 2, we'll pick up where we left off. We left off at this point, which is at x equals 1. And we're going to go to x equals 2. This time our top is g of x. And our bottom is f of x. And that would be the expression that we would use to find the area of region 2. All right, so you might want to think about how we can go about creating a single integral expression that could represent the sum of those two. That's a nice challenge. Let's see if you guys can do that. We can say the area of 1 plus the area of 2, that region, those two regions added up. We could make this one integral, starting at -1 and going to +2 of something, right? Sometimes it's f of x minus g of x, sometimes it's g of x minus f of x, because sometimes one is bigger than the other, and then sometimes it flips. So what can we do to make sure that it's always positive? Well, I hope you guys have realized that that would be the absolute value of, and the order doesn't matter when you're taking the absolute value, right? We can do f of x minus g of x, or g of x minus f of x, because it will be positive regardless. So that's a nice compact single expression to represent the area. Now, if I'm going to evaluate this by hand, then I would have to do, I'd have to break this up into these two to figure out what each one of those is and then add them up. But at this point, I'm a little bit tired of doing these by hand, and I suspect that perhaps you guys are as well. So on this one, we'll go ahead and use a calculator, just because it's at our disposal. We know how to do these by hand, so the setup is the bigger piece a lot of times with these. So when we type this into the calculator, we get, An exact value of 37 over 12. Okay, I encourage you to, at the very least, type this into the calculator and make sure that you get this exact answer, or a decimal equivalent to this exact answer. But if you're really up for a little bit of extra practice here, then see if you can get this by hand as well. It's a stamina exercise at that point, because there are so many little places where you can make a mistake. But at the very least, we've got the setup, and that is the part that we really want to focus on here.